So describing the energy graph. That is the energy graph we just looked at. We could say that heat seems to, that is heat energy, EH, seems to get stored during melting and boiling. Dissecting? Describing. It is how you spell describing. It's not how you spell dissecting. Yeah, describing. It's okay, I'll bring it lower. And if heat seems to get stored during melting and boiling, when does heat get released?
During solidification and freezing and condensation.
Yeah. Or solidification. I'll say freezing. I already started saying it. Or solidification. And condensation. Now what I'm going to be ignoring here, and intentionally ignoring because it doesn't fit nicely into our graph, but not because it doesn't happen, is sublimation, okay? Sublimation and deposition I am going to avoid. I just don't want to confuse too much here. So if I look at my energy graph, energy gets poured in. Then it gets stored up as I go through the process of changing states. And then it gets stored up as I raise the temperature of something. And then it gets stored up again as I boil it. And then it gets stored up again as that steam gets hotter and hotter and hotter. Okay, so you see these types of graphs. It looks like a staircase. And you actually, if I wanted to figure out how much energy it takes to get from this energy here to this energy here, I'd have to basically do 1, 2, 3, 4, 5 calculations and add them all up. How much energy does this represent? This, 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 and this. And then to get E total, I'd figure out how much energy I'd have to pour in to traverse each part of this graph. It's a nice little visual, and it is kind of like a staircase. Yeah?
If you had an object and you froze it, could you put an object beside it and somehow cook it with the heat that gets released or something like that?
If you put a really hot object next to a cold object?
No, if you put an object and you're freezing because heat gets released when it's freezing, right? And you put an object right beside it, could it get cooked eventually or something?
Well, if you had a cold object that you're making cold by taking energy out of it,
yeah,
then that would mean that the energy from that object you were cooling down was getting released into the environment probably. Yeah. But that would mean that the environment must be cold too, right? At least as cold as you're trying to make that thing be. That's what a refrigerator is.
Okay.
So if you put something next to it, that thing that was next to it would also get cold. Yeah, you can't hope that the radiant energy off of something that's getting cold in an environment like that's going to cook the thing next to it. But if you took a really hot thing and you put it next to something that's cold, then the hot thing is going to lose its energy, and the radiant energy is going to make the cold thing warmer. But that's kind of what a barbecue is anyway, like a briquette barbecue. Really hot things making other things cooked. Right? Okay, so we've got this graph. And so there's these two new types of energy that we're going to talk about, and we called it fusion energy and vaporization energy. So let's put that in writing. There are two types of state change energies. I'm just going to put it in quotes because it's not like an official name or anything. There are two types of state change energies. And the first one is called the latent heat of fusion. it's the amount of energy that it takes to freeze or melt. I guess when it's melting, it's releasing that energy, not requiring it. A specific mass. Okay, and so people write it as heat of fusion is equal to the fusion constant times the mass of the substance. And just like we have specific heat capacities for different substances, there's specific latent heat of fusion constants as well for every substance. Okay, and if you want to look it up in your textbook, we can definitely look it up in our textbook. I don't want to give the page reference just now. But let's look at units really quick. If this guy has units of joules, energy has units of joules, and mass obviously has units of kilograms, what would the fusion constants units have to be? Oh yeah, it could be meters squared per second squared. If I wanted to do it in terms of joules, how could I do it too? Yeah, joules per kilogram. You're right, it would reduce out to something a little bit more simple. But we could express it as just joules per kilogram, and most people do. Okay. All right, so if there's a latent heat of fusion, there must also be a latent heat of vaporization. And that involves the amount of energy required or released. I should say it properly this time. Required or released during what's the change of state here? Yeah. Evaporation or boiling, boiling point. And of course, we'd be talking about EV. We've already labeled it that. The vaporization energy being equal to LV times M. And the units are the same as for LF, for the fusion constant. It's just that it's going to be a different value because it's a just different change of state.